In this tutorial, you learn how to read audio signals from a headphone jack with a microcontroller to make your designs reactive to sound. In the description below the video, you will find a link to a GitHub repository that includes a wiring schematic, the bill of materials, and detailed explanations for each line of code. But first of all, let's have a look at a bit of theory. Physically, sound is a vibration that travels through a transmissive medium as an acoustic wave. Sound waves are rapid changes of pressure and particle velocity, and music, speech or noise are complex superpositions of sinusoidal sound waves. The amplitude of a sound wave determines its volume, and the frequency determines its pitch. In this tutorial, we are concerned with the amplitude, the volume or loudness. Loudspeaker cones or headphone diaphragms move air molecules backwards and forwards. A plotted audio waveform looks symmetrical, and the volume at any moment depends on both positive and negative domains, on the peak-to-peak level. At the zero crossing, the pressure and volume are zero. That's also where you want to cut and splice your samples when editing music. The audio signal from a loudspeaker or headphone output is a voltage that we can sample with a microcontroller's analog-to-digital converter, ADC. We sample the audio signal at a fixed frequency, but it will never correlate with the irregularly occurring peaks of the waveform. If the sampling frequency or the bit depth are too low, we can't capture enough information about the sound wave's shape. If we raise the sampling frequency and bit depth, we'll capture more information. See the effect that simply doubling the frequency and only one extra bit have on the quality of the data the ADC generates. By default, the audio signal fluctuates around 0 volts, and with around 1 to 1.5 volts peak-to-peak, headphone level output is rather low. This is why we need to condition the signal electronically and then in code. First, we shift the signal's voltage into the positive domain. At the standard 5V ADC analog voltage, we offset it to 2.5 volts with a voltage divider. However, all the positive and negative peaks, that means all the loud parts, are now above 0 volts. And how do we know where the silent zero crossings are? Therefore, we flip the negative half of the signal upwards, a method known as full wave rectification, and we capture the loudness only with positive peaks. This means that an ADC return value of 512 means silence, and everything goes up from there. We also refit the value range so it starts at 0 instead of 512. There's still an issue though. The values we get from the ADC don't use the full available range from 0 to 512. Stretching the range with a map function in code won't help, because values that weren't sampled by the ADC in the first place won't magically appear out of nowhere. We could use an amplifier circuit, but there are other solutions. To keep it simple, we keep hardware to a minimum, because the clever stuff happens as always in the code. Here's an overview of all parts in case you're not so familiar with them. You'll need the specified components, but you can find cheaper substitutes online. The wiring of all three setups is very straightforward. So, let's look at the different options. The circuit between the headphone jack and microcontroller is the same for all three. We need a voltage divider to offset the incoming audio signal. A polarized capacitor blocks DC voltage going back into the headphone AC output, and ground must be shared with a microcontroller. In the 5 and 3.3 volt circuits, both voltage divider resistors must have the same value, so we either use two low tolerance resistors or find two identical ones with a DMM. It's different for option 3, because like in version 2, we use the microcontroller's 3.3 volt output, but the offset must be half of the analog reference voltage of 1.1 volts. Therefore, this voltage divider is asymmetric. For option 1, we leave the microcontroller unchanged. For option 2, we wire the microcontroller's 3.3 volt output to the AREF pin, and we set AREF to external encode before the first analog read instruction. For option 3, we leave the AREF pin unused, but set AREF to 1.1 volt internal encode. For working with stereo, just add a second input circuit to another analog pin. While option 1 works, and option 2 is an improvement, it's obvious that option 3 delivers the best resolution, because the audio input will generate values across the whole range from 0 to 512. So, apart from using the best input circuit we looked at before, we only need a few lines of code. First, we declare a few constant and changing variables. In setup, we set the analog reference voltage to external for option 2 or internal for option 3. It is essential for option 2 before using the analog read command. Also, don't upload code with the external setting if you're using the AREF pin. In loop, we first take the time and then sample and rectify the raw audio signal until 30 milliseconds are over, while finding the minimum and maximum values within that period. It could be that for all 3 solutions, a small correction factor is necessary to bias the audio signal exactly at 512. Finally, we chart the values in the serial plotter window. Let's compare the real-world results. With a sound clip at full volume, let's see the values from all 3 setups. Please remember the original waveform. When the sound is off, audio in RAW should deliver a steady 512 for all 3 solutions. When we compare the serial plots of raw and rectified values, it's obvious that version 3 delivers the best peak-to-peak amplitude. The maximum value in each sampling period captures the beat structure and dynamics, and the 1.1 volt approach delivers the full range of 512 values, the highest possible resolution. Now we can do interesting stuff with the audio data, for example having motors, actuators or LEDs react to music, speech or noise. We look into that in another tutorial. And now it's your turn. Thank you for watching and listening.